Hey everyone, today we're going to be covering our last lesson in Unit 8, and this lesson is going to be on magnetism. And to get started, we first need to know what a magnet is. And we're all probably familiar with magnets, but maybe not the technicality behind it and exactly what makes something magnetic and how magnets can interact with each other and some of the things that we can actually do with magnets and magnetism, such as electromagnetic induction. And we'll cover that towards the end of this lesson. So to start, we first need to know what a magnet is. And a magnet is a material in which spinning electrons, let me change my color here, where the spinning electrons of that material, so the spinning electrons of the atoms of the material itself, are aligned with one another. So all of those electrons are spinning in the same direction. Now the motion of charges of these electrons relative to each other produces a magnetic force. And a magnetic force is similar to an electric force or electrostatic force, similar to gravity, what we call a conservative force. Remember, conservative forces, where we don't have to actually be in contact with something to interact with it. So the magnetic force can interact with objects without actually physically touching them. Well, even if two magnets are at rest, their fields are still interacting with each other. The electrons that make up that substance, make up that magnet, are still in motion, even if the magnet itself is not moving, and therefore it's going to exert a magnetic force constantly. Now, there's only certain substances that can make up a magnet, and most permanent magnets are made from an alloy of three specific metals. And those three are aluminum, nickel, and cobalt. That's just going to make up most magnets. One that's not listed on here is iron. Iron-containing substances can be magnetic as well. This is probably not news to anybody, but magnets do have two ends, which we call poles, generally north and south poles. And the magnetic force is going to be strongest near those poles. So if we think of a simple bar magnet, it has two poles, what we call a north-seeking and a south-seeking pole. And the force here is going to be strongest at the ends. And even if we cut this magnet in half, let's say we were to take it and we were to cut this magnet into two equal pieces. Each piece would still have a north and south end. That's not going to change. We'd still have poles, and they would still be strongest at the ends of that piece of the magnet. Now, just like charges, like poles of a magnet, repel each other. So if we bring the south pole and south pole of two magnets together, we feel that repulsion force between the two poles since they are alike. Which means unlike poles are going to attract, or opposites attract. We hear that phrase fairly often. So a north and south pole are going to attract to each other. You've seen with some of the magnets in class that we've used, some of the neodymium magnets, which are really strong, are so strong that if you get them connected to each other, they're almost impossible to get apart because that magnetic force is so strong. And if you bring those two, I have the little coin magnets, which would have a north and a south on either side. And if you bring these two close together and you have, let's say, a south and a south, the repulsion is so strong and the attraction for the north is so strong that these will actually flip around and attract to each other. Most of you have probably played with magnets before, and those forces can sometimes be frustratingly weak and sometimes really strong, unexpectedly strong. So magnetism itself is a force of attraction or repulsion between the magnetic poles of a magnet. This could be a bar magnet, a permanent magnet, electromagnet. It could also be the Earth's magnet. And yes, Earth is a magnet. Now, what you may not be quite as aware of are the location of the geographic and magnetic poles on Earth. And in the diagram here, I've written out the north and south geographic poles, which we should be relatively familiar with. But the geographic north poles, which are at, what are we going to have, 90 north latitude, 90 south latitude, are not the same as the magnetic poles. So the magnetic poles are actually a little bit offset from each other, and they don't exactly align with 0 north or south latitude. So they're not actually on the geographic north or geographic south pole, and they're actually the opposite poles. So this would be our south magnetic pole, and this would be our north magnetic pole. Now our field lines are going to run something like this. Seeking the South Pole. So if we put a north-seeking compass here, the north pole of a magnet would be seeking the opposite pole. So if we have a north-seeking compass, it's going to point towards the opposite pole, which would be the south-seeking magnetic pole, which is, not surprisingly, the north geographic pole. So as far as the magnetic pole, it's kind of the opposite of what would be, or would seem to be, intuitive. So the magnetic poles are reversed from the geographic poles, and they are not in the exact same spot. This field, the field itself there, gets produced from the iron and nickel core that's moving inside the Earth. All right, we got this inner and outer core here. And due to the movement of that liquid nickel and iron core, we create this magnetic field around Earth. And that's from the iron and nickel core. Now this region that we drew here, these yellow lines around Earth's magnet, is where a magnetic force exists. Now this region, or where any moving charged object is what we call its magnetic field. This could also be, as we said here, some type of moving charged object that's going to exhibit this field. And we'd see these lines seeking a south pole from the north to the south pole around that moving charged object or around the magnet. This is similar, like I said, to a gravitational or electric field, because magnetic fields can interact with each other without actually touching other objects. So we don't have to be in physical contact in order for this magnetic field to have some type of interaction. The magnetic flux lines are just imaginary lines that map out the magnetic field around a magnet. We call those magnetic field lines. Kind of the same thing. You can also call them magnetic flux lines. And that's going to show or map out the field around a magnet or some moving charged object. So similar to some other things that you studied in science, magnetic flux lines never cross each other, and they always form closed loops, kind of similar to the contour lines I always think of with contour maps that you study in earth science. Now, the higher the concentration of those field lines, the stronger the field is. And we see a concentrated set of magnetic field lines emerging from the North Pole. They curve around the magnet and enter the South Pole. Now, the direction of these lines, the direction of the magnetic field itself, and this is important to know, is defined as the direction that the North Pole of a compass would point in the field. That's why we see up here that the South Pole is at the geographic north, because the North Pole of that magnet is going to point to the opposite pole, which would be the South Pole, and therefore would lead us towards north if we were to actually use a compass to find direction. So drawing magnetic field around a couple different magnets here, we always have magnetic field lines that are leaving the north end, creating a closed loop, and seeking or finding the south end. And this is going to come around both ways. And this is essentially infinite. So we have the greatest strength at the pole here, and we'd have less strength where the concentration of field lines are fewer. Now, between two magnets, or between a north and a south pole, we're going to get these lines coming nearly straight across. For repulsion, now these lines coming out of the two north ends are going to come out of here, and they're going to be seeking some south pole. And we're going to see these lines repelling each other. Trying to make sure that those don't touch. And that force here, these magnetic field lines not wanting to touch or intersect each other, is that force of repulsion that we feel. Sometimes the force is so strong that we can't get the two north ends or two south ends to touch. And sometimes it's not very strong and we can actually force them together, even though we still feel the repulsion. And the force we can apply is greater than the force of repulsion from the magnets. But sometimes it's not. Now, between a horseshoe magnet, either end here is a north and a south. And our lines would run between here, or even curving out of the north to the south. Now, just to kind of put this in a little bit of perspective here, I'm going to increase the strength of our field. Now, let's first look at the magnet itself. We have a north pole and a south pole, and if we look inside the magnet, our lines here are all pointing. We got two ends, the red and the white end. The white ends are all pointing towards the south pole. And these essentially are the electrons lined up and spinning in the same direction. These are all lined in the same direction, which produces this magnetic field that we see. And we can turn this field on and off. But in ordinary materials, these spinning electrons are not lined up, so they're not producing this uniform magnetic field. Now we can bring a meter in here, and magnetic field strength is indicated by this variable B here. And the field, we got 0.9 G. As we move farther and farther away, if we get down to here, we're at 0.49. If we come all the way up to the corner here, we're at 0.19. We can get all the way up to 0.10 up there. Now, as we bring it closer towards either of these poles, we're getting a greater value. And the closer we get to the pole, this number really starts to shoot up exponentially. And we can even go right on top of the magnet, right on top of the pole, and we get a value of something around 266, let's say. And if we were to go to the other side, we should get about the same thing if I can get it somewhere right in the center there. And we're right around 265. Right about in the center here where the concentration of flux lines would be the greatest. Now this compass, the reds here are always pointing towards the south. And no matter where we bring this here, it's going to follow that magnetic field line, or what we see with each of these ones showing the strength of the field. Coming out of the north end, these are south-seeking fields, and as we move this in the direction of the field, it continues to point towards the south until we actually enter into the south. Now, if we think of this as in planet Earth, geographic north, we have North America. Geographic south, we have Antarctica down here. But that's the magnetic north at the south geographic, and the magnetic south at the north geographic. And your compass, the red part here pointing north, is always going to point towards the south magnetic pole. Let's say you were down in South America here, and you wanted to get back north. Well, your compass here is pointing not north, but in the direction of the magnetic field at that point. And if you were to start walking north here, or at least the direction your compass told you, you can start moving here, but your compass is going to change, and you can see it's starting to spin counterclockwise. And if I don't do this as quickly as I am, if we keep following where that is pointing, we are eventually going to get north. And if we were actually walking here, this might be a little more subtle. We wouldn't be moving as far east, but the compass would continually point along that field, and we would eventually just start moving towards that geographic south pole, which would get us up towards geographic north. Well, the number of magnetic flux lines, or magnetic field lines, per unit area passing through a plane that's perpendicular to the direction of the lines is what we call the magnetic field strength, which we looked at on the meter there, represented by a capital B, or what we call flux density. And that is a vector quantity, since it is described by its direction. Now, electromagnetic induction, we've seen this before. We saw this when Cole Johnson had done a demonstration showing how wireless charging worked on the cell phone that was done through electromagnetic induction, inducing a current to charge the cell phone. And that was using electromagnetic induction. So electromagnetic induction is the process of generating a potential difference in a conductor due to relative motion between the conductor and a magnetic field. Now, if the conductor cuts or moves across the magnetic flux lines, then the magnetic force acts on the electrons in the conductor and causes them to move from one end to the other. And this is where we get our potential difference from one end of the conductor to the other, which is going to cause a flow of electrons, or it's going to cause a current. The difference in potential created in the conductor due to its relative motion in the magnetic field, that's what we call an induced potential difference. It wasn't there, but we kind of created it or induced it into happening or into occurring or being created. And this is real simply what this looks like. We have a horseshoe magnet here with magnetic field lines going from north to south. And if we take this wire, measuring voltage here, take this wire and we move it up and down across these field lines, or cut across those field lines perpendicular to the field lines, we induce a voltage from either end of this conductor, which causes an induced current to flow through the conductor. Now, to give you an idea here, this is a simple coil of wire in which we have a voltmeter connected to either end here. And by moving this magnet, cutting across the field lines of this magnet, which we can see coming out this way, so we can cut across these perpendicularly, we can create a voltage here on either end of this coil of wire and cause a current to flow through it to power this light. If we move this through here, we see the induced voltage, the induced potential being created on the meter, and we can see the flow of current through the light bulb. Now, the more coils of wire we have, and the faster we move this through here, the greater the induced potential difference we can create. So if we were to use a smaller coil of wire and the same magnet, we're going to induce a smaller potential difference around that wire or through that wire or at either end of that wire. We can see that by the current flowing through the light bulb. Now, if we just leave this magnet in the wire, in the coil, it's not going to do anything. It has to be moving or cutting. And this is what we're getting in a generator. And this is happening very fast. This coil of wire, or the magnet itself, is spinning. And the faster we can do that, and the greater coil of wire that we have, the greater the potential difference, the greater amount of current that we can produce. Now, if the conductor that we just saw there is part of a complete circuit, then we can have an electric current be induced. We can then use that to power something. If the conductor is moved parallel to the lines of flux, then there is no induced potential difference and no current is produced. Meaning, if we were to move this wire left to right in the same direction as those magnetic field lines from North Pole to South Pole or South to North, we're not going to have an induced current or an induced potential difference that has to cut perpendicular to the magnetic field lines wherever they exist. Now, electromagnetic radiation, which we'll talk about a lot more in our next unit, is produced by oscillating or accelerating electric charges. And those two produce alternating or changing electric and magnetic fields that are going to radiate outwards from that point into the surrounding space in the form of waves. And we call those waves, the combined electric and magnetic wave, a electromagnetic wave. And we'll focus a lot on electromagnetic waves in our next topic. If you guys have any questions, make sure you write them down and make sure you ask them and get them answered. Hope you all have a wonderful day.